This is the last video in which we will be discussing the theory behind how you can go about solving the one-dimensional Schrödinger equation for the Poschl-Teller potential. And in this third video, we will discuss this new approach called physics-informed neural networks, or PINNs. And you see that in the parentheses I wrote 21st century because this is brand new, guys. And I became interested in this because I am actively working on a research problem in which we are trying to use machine learning to do some physics predictions, let's say. And I tried to build into my model some physics, meaning that I tried to take into account the physics of the problem when building these machine learning models. And by, I don't know, researching various papers and YouTube videos and so on related to how one can introduce physics into a machine learning problem, I ran into this guy who is professor, I think now, at Imperial, I think, in London. And I found this video that is 2 years old, but okay, I found it now. And I will provide a link to that video. And in that video, they introduce PINNs, and they use them to solve the Newton equation for the harmonic oscillator. Okay, that's a different thing. But based on what they discuss in that video, I built my own physics-informed neural network, which I'm going to show you in the next video probably. But anyway, okay, let's go and see what PINNs are. Okay. And keep in mind that, again, we are solving this one-dimensional Schrödinger equation for the Poschl-Teller potential, okay? And we have seen how to do that using the direct solution, the matrix diagonalization approach, sans the code. Okay, I need to show you the code and how this works in practice. And now we're going to go discuss the theory about what PINNs are and how you can use them to evaluate wave functions, okay? Let's go to a clean page. So let's go here, okay, which is the last page of the previous video. Okay, and let's write down 21st century physics because I don't know, I found it cool. Okay, PINNs. Okay, and as I said, PINN stands for physics-informed neural networks. Okay, so this is a brand new approach as far as I know. I don't know. Nobody used this 10 years ago. I think it's safe to say. Maybe 15 years ago. I don't know. But never say never. I don't know. Search the literature. I haven't done an extensive research on this because I got excited about how you can implement this for the Schrödinger equation. So let's write down what a PINN is. So a PINN, a physics-informed neural network, is a neural network that learns solutions to differential equations. And recall that most problems in physics, if not all, can be cast into a form that involves a differential equation, right? I mean, in quantum mechanics, you have the Schrödinger equation. In classical mechanics, you have the Newton's equation, the Newton's second law. I'm sorry. Then in electromagnetism, you have Maxwell's equations that you can solve using differential equations in some cases. Like the first thing that popped into my head is waves, like electromagnetic waves in a cavity, maybe. Then the heat equation is a differential equation, and so on, okay? So there is an extensive list of differential equations that describe physical problems. And not only physical problems, I'm pretty sure you can use the same approach in chemistry and biology and other fields that involve differential equations. So physics-informed neural networks, let's continue. So what does this do? So it combines supervised learning supervised learning from known data, and actually let's write this as 1, and then 2, physics constraints here the Schrödinger equation, of course. And this part is called, you can call this as self-supervised learning. Okay, I'm assuming that you are a little bit familiar with machine learning. So in machine learning, there are two types of problems, supervised and unsupervised problems. So in supervised learning, we know, we try to predict a function y, okay, using some data x, okay? So, but we know the data x, and we have the values of the function y at some points x. So for example, here, if we are calculating a wave function that looks like this, okay, this is a Gaussian pretty much, then x's will be, I mean, x and y's are these points here, for example, okay? So this is your x, and this is your y, okay? The y are the labels, and the x are the features, as they are called in machine learning, okay? And then you have unsupervised learning. In unsupervised learning, you only know, sorry, let's delete this. So in unsupervised learning, if you're trying to learn this function again, which is a wave function, you only know the x points. So you're given only these points, you know nothing about y, and you try to predict it, okay? And then this problem in which we are calculating a wave function is called a regression problem, okay? Because you're calculating a function, whereas there are also classification problems, which are yes or no problems, okay, in machine learning. So anyway, physics-informed neural network predicts solutions to differential equations using partially supervised learning from known data and physics constraints. So why do we do that? Is the next question. So why would you do that? Why do you need why not just calculate the function using data and get done with it? Like why not just solve the differential equation and get this data? This is what I'm trying to say. So the reason is some equations are computationally expensive. What does computationally expensive mean? It might mean that it might take weeks to solve. It might take lots of resources, like you might need a supercomputer, GPUs, a computer cluster, something like that, something that costs money and time, money or time or both, okay? So maybe you want to, so maybe you can obtain a few data points okay, and then use machine learning using the actual data points and PINNs to obtain an accurate solution faster. So what I mean by that is, okay, your goal in quantum mechanics is most of the times to obtain the wave function, because using the wave function you can calculate other quantities as you like. So maybe this is your wave function. Okay, so your wave function might be something that looks like this, that you want to obtain, but okay, because it's computationally expensive, maybe you get this data point, because usually you solve differential equations on a grid. Okay, so you divide your x-axis into intervals. Okay, and maybe you calculate the wave function for this point, and maybe this point, and maybe this point, and that's it. You got tired, you're sick of it, and you're like, okay, I'm not gonna do anything else. So you only have these data points, and then you still have your grid on which you want to solve this differential equation. Okay, we're gonna come back to this later. So you can use the following approach pretty much. So let's keep talking. So you have two types of data. The X data, Y data, okay? So these are your labeled, so labeled data, okay? So if you build a neural network, you will use this data and calculate, as a loss function, you're gonna use the squared error as usual in supervised regression. Okay, and the second type of data is physics points. So physics points, which we will call xphys, xphysics, and this is nothing but those intervals that I wrote here, that I drew, sorry, on this plot. So these points, this will be your xphys, the physics points. So you only know x in this case, you don't know y at all, okay? And this data with the crosses will be your x data and y data, okay? So this is the supervised part, and this is the physics part, okay? So for the physics part, you only know, so you only know xphys. Okay, so no y label. You don't know that at all. Okay, so how do you approach the problem? So you pass xphys through the network to obtain y PINN, okay, which is going to be your y phys. Okay, so you don't have labels, so the only way to obtain labels is to pass those grid points through your network and calculate a wave function, pretty much. Okay, then the next step you need is to calculate y prime and y double prime, so the first and second derivatives on the grid using AutoGrad. So for this implementation, I'm going to be using PyTorch, and PyTorch has this function called AutoGrad that calculates the first and second derivatives of functions using finite differences, pretty much. Okay, we will see that in the notebook in a while. Okay, once you calculate the first derivative and the second derivative, and because you have the form of, and by the way, it's, to be more accurate, this is y prime PINN and y double prime PINN, okay, to be more accurate. So once you take your physics points, you pass them through the network, you calculate the y PINN, you use the y PINN to calculate the first and second derivatives, and then you plug into this expression r of x, and r starts for residual, which is equal to -1/2 times the second derivative PINN plus V calculated on the physics points times Y PINN, and this must be, minus E, which is another parameter you need to predict using the network, times Y PINN. And you can recognize this as the Schrodinger equation, right? So this is the Schrodinger equation if I bring everything to the left-hand side. So it's the Schrodinger equation in this form, minus 1/2 y double prime plus v times y minus e times y, this should be equal to 0. Okay, so using the physics point x physics on the grid, the calculated wave function on that grid, and the calculated derivatives, we can calculate the value of that expression r of x, which is the residual. Okay, if r of x is not equal to 0, then y PINN violates the physics of the problem. I hope this makes sense. Okay, so to fix that, you adjust the parameters of the neural network and try again. Okay, so r of x becomes the guide, or in machine learning lingo, the physics loss function okay, so it becomes the guide or the physics loss function in calculating y. Okay, to be honest, this is something I tried for the first time in my life this week. Okay, I mean, I have worked in machine learning problems, including having some publications in the field, and I have worked in nuclear theory, so I'm familiar with the Schrodinger equation, etc. But this is the first time I tried this, and it worked, and I'm kind of excited about it, and I hope this makes sense. So you pretty much use two loss functions when you use PINNs. Okay, the first loss function is related to the typical loss function, the squared error function that you use in neural networks. Okay, and most people in machine learning are familiar with that. But you add a secondary loss function, and the secondary loss function is the Schrodinger equation itself evaluated on the points for which you calculate the wave function. Okay, so the workflow is the following. Okay, at each training step, we do 2 forward passes. Okay, first we pass the data for the labeled data, so x data, y data, okay, which is the supervised part. And then in the secondary pass, we just pass x physics, we calculate y physics, and then we calculate the residual. Okay, and we pretty much use a total loss equal to some weight data times loss that comes from the data, and this is the squared error loss, plus some weight for the physics part times that residual. okay? And usually W data and W physics are equal to 1, but you can play around with this as you do with neural networks, and you can put an emphasis in the data, in which case you take the weight of the loss function for the data to be higher than the weight for the physics part, okay? So the optimizer updates the neural network parameters plus the energy in each step. So hopefully you get an iterative improvement of y, okay? And this is it for this video. We discussed the third way in which you can calculate a wave function. And now we will hop onto the notebook. Actually, no, we're not gonna do this in the same video. I will actually have a fourth video that is gonna be a demonstration of all these concepts through a Google Colab notebook that uses Python to do calculations for us. Okay, I hope this is useful. I'm gonna provide links to Professor Benjamin Moseley, the guy who inspired me to do this, to use this method with the Schrödinger equation. And I will probably provide links to papers you can read and learn about this method. So yeah, we are living in exciting times in terms of physics. Okay, there are no jobs currently. Okay, that's a pain, but there is a lot of development in new approaches to solving physics problems. So, okay, I'm gonna stop the video here.